Today I'm going to demonstrate how to derive the famous Boltzmann distribution law by using some of the formula you might have learned in high school, namely the permutation and combination formula. Okay. And in addition, of course, we have to use the idea of calculus. Okay. And together with what we call the Lagrangian multiplier. Okay. Together with this, by using all these tools, and we should be able to derive this famous distribution law, and in short time. Let's go. First, we have to describe a formula. We have to introduce a formula as a basis of this derivation, so that you can use n equal to n factorial divided by n1 factorial, n2 factorial until nr factorial. Okay, so this is a formula you learn in the permutation and combination. In particular, it is dealing with this n represents the number of arranging n identical objects, in our case, identical particles, into R groups. Each group will contain respectively n1, n2, and nr numbers particles. Okay. Before we go further, can we just rewrite that formula into a more compact form? N factorial. I use the pi notation. When you use the pi notation, we can just use this simplifies. Can we use a k here? K is a discrete variable, k factorial. That is a k from 1 to r. So this formula can be used to derive the Boltzmann distribution law. Before we go, perhaps it would be helpful to draw this diagram to illustrate what we are going to do. In this diagram, I have drawn several energy diagrams. Okay, represent each subgroups of this arrangement. And if I just label this vertical one as energy, so these are energy. So energy from say from 1, 2, 3, and so on until this is until you got R, all of them, you got R subgroup. And then we place these identical particles in each of them. Okay. Of course, there are more than one way to do so. Here I just draw one of them. Just draw one of them. Okay. This is just one of the arrangement you can do with these n identical particles. Now, if I use the profile or envelope to illustrate this distribution, you will see that clearly in this case, you will see this kind of distribution, right? Of course, this distribution or configuration, I prefer use the word configuration. It's just one of them. There are more than one. There are more than one configuration or distributions. So if I just added one more different distribution graphically, so you can see that it is likely. It's also acceptable. Okay. In addition, in physics, we are more interested to find out the most probable configuration or most probable distribution in order to solve the problem in thermodynamics. Okay, because we are interested to find, so that is our objectives. So our objective is to find the most probable configuration or distribution, configuration, distribution. It's the same, distribution. I still prefer to configuration, the same. It's configuration is just its pattern. So once you place certain number in each group, you will see these patterns. Of course, in terms of probability distribution, it is distribution. Right hand here is a configuration. Of course, the most probable configuration is unique, is one. That the criteria to find this distribution is, according to calculus, is to find the first, is to net the first derivative equal to 0. Okay. So because this function, the mathematical expression is complicated, okay? So in history, and Boltzmann was first to propose that instead of use the first derivative of n with respect to the variable, he suggests, can we just use log? Okay. Before that, can we just write the n in the natural log form? So n is natural log. If I apply the natural log, then the formula for the n, capital N, can be rewritten as L n factorial and minus and n, that's can we use log here? I use two step. Natural log, that is pi, that is nk factorial, and k from the same, k from k equal to 1 to r. Okay. So by the way, what is this n? So n is the total number, is the total number of the identical particle. That is a total number of like or identical like particle of particle. Okay. Now use a little bit of the logarithmic law. We can simplify the second term a bit. So we can, that's this first term. The second term can be simply replaced by sigma form, the summation. So that would be the sigma log nk factorial, k from 1 to r. Okay. So this is here we have used, if you go back to that logarithmic law, you can understand this step. Okay, but this is the first step. This is the first simplification. So the first simplification. The second simplification is using to, if the n is large, so if n is large, okay, it's large numbers, we can use what we call the Stirling approximation. So we can write this, so log n factorial can be approximated as n multiply log n, take away of n. Okay, this similarly we can apply this approximation called the Stirling approximation. Can write down here. So this is called the Stirling approximation. I can show you how to obtain the Stirling approximation on the other videos. Okay, and so similarly, we can apply this Stirling approximation to the second term as well, because normally we are dealing with large number of particles. It's much larger than Avogadro number, which is 0.2 multiplied 10 to the power of the 23. That is a 1 mole. Okay. So that number is large. So that is justification to use the Stirling approximation in this context. So the second term, this is the last term, the first term. The second term, ln nk factorial can be also approximated as nk ln nk and minus nk. Okay. So after this, the two-step simplification, then we can find the first derivative. Okay, let's find the first derivative. So let's just go to find the natural log n first derivative. It's called the partial derivative with respect to a particular variable. Can we call the ni? It is important to use a different subscript here because ni is one of the nk. Okay, so nk range k change is k is discrete variable. K change from 1 to n. One of them is I. Okay, so we differentiate these two variables. So the first term, if here we can simply apply the product rule in the calculus in order to find the first derivative of function. So we can get n over n multiply n log n and take away of the, in this case, and we have to be careful that this is when we apply this log n here, we have actually, can we just write down here, we have actually doing this partial derivative ni, in which so what does this n? So n, the n is can be rewritten as a sigma. Can see in here we have introduced the constraint here, so we have rewritten n into the sigma form. So that is nk and k from 1 to r. See, so this is k from 1 to r. That is nk. Okay. In this way, we know that there's only one n is non-zero, which is called ni, which is not zero. Other n are independent. So therefore, we can rewrite this as the first term is 1. You see, we got plus log n, and the third term is partial derivative ni with respect to the ni. Other term vanished. Okay, so therefore the sigma notation vanished too. Okay, of course this term just equal to 1. So therefore we can get this simple formula n. Okay, so similarly we can, if we apply this same argument, we can also obtain log the second term. Can we go to the second term? So we can apply for this for the second time. We have simplified that before we go further. Can you see? We have to, can we call this A? I jump. Can we call this A? Can we call this B? All right. So basically, in order to find this one, this is actually, this is not n, it's just n. It's A here, you see, A here. A represents these two terms, and that will give you the single term. And the fourth step is we found the B. Here I have introduced two variable A and B. So that's equal to ni. This time, the first derivative is applied to the sigma form here. So that represents the sigma. Don't forget that there's a sigma here. So that is sigma, that's the first derivative in I. That is a sigma log nk factorial and k from 1 to r. Okay. Same argument that among these n, only ni can be treated as a variable and other terms are independent or are constant, so therefore vanished. So the sigma vanished. It becomes n. We just write a result here. Just can we just write a result here? The treatment is the same. So we got log, eventually we got n I. So fifth step is just combine them. So therefore, that will allow us to work out this first derivative. Okay, the first derivative of log capital N with respect to the ni were equal to the difference of these two terms. So one is log n, another is log ni. You see, ni, that's ni. Okay, combine these two terms into one term, we can rewrite it as a log n over ni. Okay, that is very important equation. Can we call it equation 1? Okay, of course, in general, in many cases, we can apply this criterion to find out the most probable distribution. Okay, that is our objective, to find the most probable distribution. Okay, so many people, you might think that this just net equal to 0. We have found that. Can we just net that equal to 0? We just net that n equal to 0. Okay, the first equal to 0 in order to find the most probable distribution. But I have to put the question mark here. Can we do that? Because in our case, in addition, apart from the given formula for the capital N, we have constraints. Okay, one constraint is here. See, this is one constraint. Namely, the total number is constant. Okay. The summation of this nk were equal to n. There's another constraint. It's called the total energy of the system. So how to write this constraint? So we just simply say the total energy can be written as sigma. We use the number of that identical particle in the group or in the particular energy group or energy level, and multiply the value of the energy of this particular energy level. Can we call it epsilon k? And these are two constraints in order to find the maximum. Okay, so the maximum, in other words, this optimization or the maximize to find the maximum value is under special conditions. It's conditional. So therefore, in this case, we cannot use this conventional approach to find the most probable distribution. What can we do? Well, some clever mathematician had provided the solutions or methodologies for us. That is called, we have using Lagrangian multiplier. So Lagrangian multiplier. I think you have heard this terminology when you studied the high-level the calculus, multiple variable calculus. Okay, Lagrangian multiplier is used to solve this type of problem. So instead of just consider the first derivative of this log, in our case, a log n, that again with respect to the ni. So that is the first term, that's a log n. We have to put the two linear terms. One is alpha multiply one constraint. That constraint is nk, and k from 1 to n to r. That is the total number. Okay. Another constraint is energy. Can I put the beta here? That would be equal to, and that would be the nk multiply the epsilon k, and the k, the discrete variable, from 1 to r. Okay. We have to use this condition in order to find the most probable distribution or most probable configuration. Okay. So doesn't matter, we can do that because so far we have done the first. Okay, so on the first page we have done that. So we have first to know that n partial derivative log n, and with respect to n I is simply equal to log n over ni. Okay, double check. Okay, we just found that. Got this one, n over ni. Now we only need to find out the first derivative of the next two terms. Okay, so alpha and beta can be considered as independent factors called, oh, by the way, in our case, alpha and beta are called Lagrangian multipliers in our case. Okay, so we need to just work out this one by one. So we need to find the first derivative of sigma nk and k from 1 to r with respect to the ni. Okay, we have dealing with this first derivative before, because in which among these n, k, only one is identical to ni. So therefore, this term can be simply written as ni with respect to the ni, which is unit. Okay, so the sigma vanished. In addition, okay, we can deal with the first derivative of this term, that is a sigma nk multiply epsilon k divided by, before that, k equal from 1 to r always, okay, always. So that is r is the number of the energy group or energy levels given for this kind of arrangement. And with that partial derivative with respect to, again, with ni is one of them. Again, we can make the same, by the same token, we can argue that the only I term remain, other will be vanished when you do the first derivative. Okay. So we can just simply written this as nk, and we can put the ek out in front, because ek is different, independent from nk. So ek is, in this case, is constant. So that will become n. Oh, sorry, not k, but I just, it should be just I, because among these different n, only n sub I is non-vanished. So it's ni. Similarly, this term became unit, so we got ek. All right, so if you take these three terms into account, so these criteria, they generalize. This is this constrained criteria using by invoking Lagrangian multipliers, we can get this condition. So we got n. So we got n log n over ni. The n is the total number of these of the identical particle in the system. Could be the number of gas. We're equal to, can we just write it here? We're minus alpha and minus beta epsilon I. Oh, here's not k, it's I. This is not k. Let's be careful. So this should be I, not k. Because k, if k is not equal to I, it should be 0, right? So we have to, this term vanish. So only I left. So okay, that is consistent now. And these three terms must be equal to 0. Okay. Now, before we go that, can we just rearrange that as a negative? Can you see, because this is negative ni over n minus alpha minus beta epsilon I. Okay, and then we shift that term on the other side. So what we have, remember, is ni. So therefore, we got ni divided by n equal to negative alpha plus beta epsilon I. Epsilon I represents the energy of particular energy level, or the particular energy group in this case. All right, we're almost getting there. Hang on, we have put we forgot the log here. We have put the log here. Okay. a little bit of high school mathematics. So what we do, we just multiply 1 here, okay, and rewritten this one as the log E, okay, alpha plus beta epsilon I and log E, and then move this back to this index, okay, so that will become log E negative alpha plus beta epsilon I, okay. So that's how we can simplify this mathematical form. So what can we do? We just simply remove the log, okay, remove the log. Then we got what we want. It is a famous mathematical expression known as Boltzmann distribution law or Boltzmann law. That is Ni, n will equal to E, okay, negative alpha plus beta epsilon I. Okay, if you can rewrite the left hand side into as epsilon negative alpha, you get this negative beta epsilon I here. Yes, so in this case, you can get it. The number in a particular energy group will equal to the n, the total number, multiply a factor exponential function. And in this case, I have to put this, I can just put a constant here to represent this chemical, the constant, the chemical C. We just put a C here, and that became negative and beta epsilon I. And so that is Boltzmann distribution law, okay, distribution law. Of course, if you know the background, a little bit more background about the thermodynamics, the beta factor here can be written as 1 over Kb, multiply the T. T is the absolute temperature. So what is Kb? The Kb is Boltzmann constant. So Kb is Boltzmann constant. So therefore, we got this result. Ni will equal to n multiply constant, exponential function, and epsilon I, and this kT, kBt. So that is a famous law of Boltzmann distribution law. It is a famous law. I hope you will find this derivation interesting, because we have apply even some formula actually you have learned in high school, but I don't think your teacher will explain that actually we can use these arrangement formulas to actually derive the famous Boltzmann law. Thank you.